Welcome to Study Loop.
This is chapter 21, problem number 66. In part A, we are asked to calculate the RMS current. And we are given the frequency as 60 hertz and the RMS potential as 120 volts. And the resistance is 2.8 kilo ohms. And the inductance is 350 millihenries. So in order to get to the RMS current, we need to divide the RMS voltage by the impedance, right? Where we know that the impedance equals to R squared plus the inductive reactances square, right? So we know that the inductive reactance is 2 pi f inductance L. So we put everything back in the RMS current equation. So the RMS over then R squared plus 2 pi f L squared. So RMS current is given to us as 120 volts, and the resistance is 2.8 kilo ohms. So let's convert that to ohms square plus 2 times 3.14 pi, right? The frequency is 60 hertz. And we have the inductance. If we convert this to henries, it's going to be 0.35 henries, right? 0.35. And then we're going to square everything. So our RMS current is going to turn out to be 4.28 times 10 to the power of negative 2 amps. Now, part B, we were asked the phase angle between the voltage and the current, right? Phase angle. So in order to get the phase angle, phi is going to be equal to the inverse of tangent, the inductive reactance divided by the resistance. So then we can plug in 2 pi FL for the inductive reactance divided by the resistance, right? So inverse 2 times 3.14 times 60 hertz times 0.35 henries divided by 2.8 times 10 to the power 3 ohms. From here, the calculation is going to show us that the phase angle between the voltage and the current is 2.7 degrees. So in part C, the power dissipated. So the power dissipated, as you know, is proportional to I, the square of the current times the resistance. And in this case, we have the RMS current, right? So then what we calculated, our answer to part A was here, 4.28 times 10 to the power of negative 2 amps. We're going to take the square, and then 2.8 times 10 to the power 3 ohms. This is going to be equal to 5.13 watts. Part D, we're asked to calculate the RMS potential across the resistor and the inductor. So the RMS, let's start with the inductor, right? That's going to be equal to the inductive reactance times the RMS current. And again, let's plug in for the inductive reactance 2 pi FL times I RMS then. So 2 times 3.14 times 60 hertz times 0.35 henries times 4.28 times 10 to the power of negative 2 amps. We have the RMS potential across the inductor as 5.65 volts. Now, the second part of part D is asking RMS potential across the resistor. So then that is going to be equal to the RMS current times the resistance, right? So it's going to be equal to 4.28 times 10 to the power of negative 2 amps times 2.8 times 10 to the power of 3 ohms. So what we have is 119.84 volts. Since there is a phase difference between the two, then you know that the RMS potentials are not corresponding to the same value.